All right, so my name's Ken. You can just call me Ken. I use they, them pronouns, and this is environmental geochemistry. And there's a ERTH version, there's a cross-listed SUST version, and there's a grad version. And all of them share the same content here in class. The grad version will have some slightly different assignments at some point. You know, like a little bit different homeworks, slightly different grading rubric, but everyone's working together on the same content. There's a web page on the department's website that has the syllabus, but the syllabus is also available through Lima and through the department's syllabus webpage, so you can get it a bunch of different places. In the syllabus, I also have embedded in the kind of tentative schedule of what we're going to do this semester, plus minus. Like I always somehow mess up on the days of holidays, so sometimes something gets shifted by a day or something. You can find that online here. I think I forgot to put it up on Lima, but I will, so if I already forgot. So I will do that. And what you'll see is that we're going to cover some like topics that will kind of be a natural flow from one thing to the other. For most of the semester, we'll be talking about things that involve interactions at the land surface, a lot of water, a lot of biology, a lot of interactions with particles, organic matter, organic chemistry. And then kind of at the end of the semester, we're going to switch and we'll have like a few weeks where we'll talk about the atmosphere, acid rain, ozone layer, global warming, those kinds of fun things. And then at the very end of the semester, we're going to have a couple of weeks where we're talking about environmental radioactivity. And so those will be, they will tie back into the bulk of the class, but that stuff will happen later at the end. And so as always, you know, use Lima for stuff. Lima, I like, I don't know how you guys feel about it, but I hate it. So there's 3 different instances for this class, and I can't like put stuff up once and have it go to the others. Sorry, it's just flaky. Try to put everything up there. I will put a PDF of the PowerPoints that I do in class up there, so you can pull them down and check them out. Sometimes I'll put other reading up there. Sometimes I will do other things through there. Like right now, I put up a poll that just asks a question about whether or not you want all the content live or you want to see some videos, and then we talk about them here in class, and it's kind of whatever you guys decide. But I will tell you now that I'm not sure why this is doing that. That I have like a week where I'm going to be in New Zealand at a conference at the end of the month, and so there will be 2 iterations of class that are kind of whatever remote, if you will. Any questions about any of that stuff? Okay, so this is just to show you that like the way everyone sets up their Lima a little bit differently. But I'm going to put under resources, you'll find all that stuff that I just told you. The link to the schedule, the link to this Zoom if you want it. And then there will also be folders under resources, and there's one that says, I think, lecture notes, and one that says videos. And so I'll put the videos and the lecture notes in those 2 things. This is the text. So I think there was like a bit of confusion. What version of the text did you guys get? 10? 10? Okay. Because there's a new 11th edition, which they didn't send me. And since I didn't get it, I asked to just keep using 10th. And so up until that 11th one, this 10th edition was like super expensive, like $75. And the 9th version you could get like on Amazon for like 10 cents. So if someone wants to use 9th, they can. Here's like a table that just sort of shows the difference between the 9th and the 10th is that they took a chapter out and they moved it somewhere else. So then all the other chapters are like a different number. So I haven't looked at the price of the 10th edition since the 11th edition came out. And if any of you is using the 11th edition, let me know, and I will look at it, try to get my hands on it and see if it's different. But I've been using this book since the 6th edition, and it doesn't change by very much. It's just like the way the company makes money. And so, like I say, this chapter 2 got moved into chapter 16 over here. So all these chapters go up by one number between 10 and 9. And that's what the 10th edition looks like. So there's going to be a midterm. I tell you now ahead of time, it's a take-home thing. I don't do in-class stuff on a time limit, so you'll have time to work on it. Usually kind of right before or right after spring break, somewhere around there. There's homeworks. They'll maybe be 4 or 5, depending on how ambitious I get. And then there'll be a final paper, and the paper will be on an environmental topic of your choosing, right? And there'll be some parameters, sort of like describing a contaminant in a couple of different environments, like acid rain in the atmosphere and in the soil, or something like that. Or you can compare 2 different contaminants like lead and dioxin, and for instance, in tuna or something like that. So when we get there, you'll see. And each one of those accounts for about a third. I'd like you to turn stuff in on time. I'm also time challenged with everyone else. So I understand if you have like a real serious thing coming that you can't do something that week because all your classes have stuff to do that week, but just let me know ahead of time and we'll arrange something. But if you don't tell me, and then whatever, like 3 weeks later, like, oh, I got this homework I want to turn in, especially if I've already turned back the other graded ones, then I'm not going to take it. And or if I haven't turned back the other ones yet, I'm going to apply a penalty. So check in ahead of time. That's all I'm asking. Attendance, as I said before, I kind of expect you to attend, but if you can't, that's okay. It's not officially up here in the grading rubric, but it does can count in borderline cases. And of course, I'd like you to participate. So I put this poll up I mentioned, which is to ask you, what is your preference? Because, we can do these this way where it's entirely live. There's a little bit of time for Q&A, or I can try to prepare some of the content that you watch ahead of time, and then we can talk about it. Like I say, it's up to you. I kind of want to hear at different years, I get different. It's never all one or the other, but sometimes you try to do a few of these this way anyway, where we get the content out and then we can discuss it. But I'm interested to hear what you all think about that. So that poll is open all week. It's like, a way to play with La Lima a little bit. There's also, this new thing that they've added, which can't remember what it was called, weekly engagement thing, right? I'm required to do it the first week. It's like a university requirement to show that you attended. I'm not going to do it though. I mean, do it this week because I have to, but then after that, you can just ignore it. I'm not counting it for anything. It's just on there and I can't erase it, can't delete it. So when you go up there and you see it, do your this week one and then forget about the rest. For reading, it'll be in the text, but, and this is a frame grab from this instance of this class last year. I'm just realizing I forgot to upload this. There's some background reading that doesn't exist in Manahan anymore. They stopped putting it in the 7th edition. So there's a background on kind of fundamentals of chemistry. It's just meant to be like, here's everything you learned in chemistry in case you forgot it. And there's another one on organic chemistry. And I'm going to put both of those up there. This one, it's not there yet, but it's called Chapter 28. And you can flip through it and like, oh, yes, convince yourself I know all those things already. Or maybe there's a chapter in there or a section like, oh, equilibrium constants. Let me remind myself, right? I'll try to explain any of that stuff. And if you have questions during class, totally ask. But it's meant to be a reference. And so I've kind of made that as additional reading for today, or for this week anyway. And this organic chemistry one will be for later. We'll talk about organic chemistry in a few weeks, but I'm going to put it up there now. And I don't remember why. Oh, there's also this optional self-study chemistry review. It's a few slides, maybe not a few, something like 30 in a PowerPoint that is like, here's the stuff I think you for sure want to know. It's stuff like how we write out equilibrium constant, how do we balance chemical equations, some really intro thermodynamics-y stuff. Can't remember what else, but that kind of stuff. And again, it's like kind of at your, check it out if you want. And what I would say is, for some people, it's been a while since they had that stuff, and so it might be like a little bit rusty. So use it to like spark your imagination. And if you're like, I can't remember that, then just ask. Because I just want to make sure we can use the language of chemistry here without, any confusion. There's also a table, which is basically, it says Manahan edition 10 versus edition 9, which is basically that thing. This like blown up so you can actually see it. So you can look and see if you're using edition 9, what's the story with the differences. And so like I say, this is note to myself. If you check on La Lima now, you won't find this stuff. Anyway, I will try to get it there. And I don't remember why I put this version of, I have to look at this. I can't remember what this chapter 1 was from edition 9, why I had put that in the folder last year. So I can't remember. Okay. Anyway, any questions about the class, logistical type stuff? No. Okay. So, the rest of the time today, just gonna introduce you to what we're going to talk about in class. I hope you're taking this class because you're interested in the content. I'm super enthusiastic about this topic and about understanding kind of in both ways how we use chemistry to study the earth, how chemicals in the environment impact us, both from the natural and the non-natural perspective. A lot of times we think about this as a sort of a binary situation, but it isn't. You can have natural chemicals and non-natural composite concentrations that are really as harmful as anthropogenic compounds. Some anthropogenic compounds are super hazardous in very small quantities, others only in large quantities. Some of them have very direct measurable impacts where you put something into the environment and you see what it does. Other times one thing perturbs something else, and the effects are a lot more difficult to see. But it's only by sort of understanding the whole package that we really start to get a feeling for how humans are perturbing the environment. And I'm, one of these people that believes that we've fundamentally changed pretty much everything about the way the Earth operates. There isn't an ecosystem on the planet where you cannot find anthropogenic chemicals. Whether or not they're having a net negative impact is something that we leave to specific study. But we know the chemicals are there. The deepest parts of the ocean, the frozen tundra, animals living near the poles, in the deserts, highest tops of mountains, there are anthropogenic chemicals that we invented as recently as the post-World War II era, and we find them there. So they're there. They're high up in our atmosphere. They've changed many fundamental things about the atmosphere that at one level allow for life on the surface of the Earth. So the question is not, how do we stop all that, because that is humankind's progress. The question is more, how do we understand the impacts and try to make smarter solutions for the future to both mitigate the things that we've done and to prevent new things. And we have a long way to go. And again, I'll soapbox here for a second. This is my political opinion. Money pretty much drives all these decisions, and how much money a company is going to make, how much risk is a government going to take to prevent actions that are based solely on money because they are negative on the environment. And as we all kind of know, our world has gotten complicated where those two things sometimes work together. But we're going to focus on the science aspects. And I think what you'll find is that we know about harmful chemicals, we know about harmful impacts on the environment long before there are regulations in many countries, especially ours, that say we're going to do something about it. So it's useful to be aware, if nothing else. And I think, like a lot of other arguments in science, some of these are not cut and dry. There's some nuance, right? There's some trade-offs. There's some gray areas at the degree of sort of our uncertainty about the impacts in some environments. And there are people that use that uncertainty to exploit it to prevent change. Global warming change is the perfect example. The science has been pretty much set since the 80s. We've known what was going to happen. perhaps not the details of the magnitudes, but you just look at, what the fossil fuel industry did and what governments did, especially ours, to prevent action at a time when action could have actually helped us much more than it can now. And this is true with many examples. We'll also look at some examples, though, in the sort of preceding period, the 60s and 70s, where I don't know, there wasn't quite as much cynicism. And so three things that were attacked successfully: ozone thinning, not completely, but to some extent, the limiting of chlorofluorocarbon emissions to the atmosphere, acid rain from burning of contaminated fossil fuels was curtailed for many decades. Unfortunately, it's now coming back because of global energy demands. And phosphate loading into the environment, primarily through soaps and detergents, which were causing lakes to go eutrophic around the world, especially in North America, and having really negative impacts on aquatic ecosystems. And those were three things that we we were able to put some logical controls on and prevent what could have been catastrophic impacts. So in all those cases, this kind of distinction between what is the natural distribution of chemicals in the environment and how are we perturbing them, and how have we added things to an environment to perturb them, are super important, right? You have to be able to make the arguments, and that requires data. And we're in a kind of a golden age, I would say now, of data and observations. We are experiencing a world in which people are developing cheap, inexpensive, easy to deploy sensors. We have cellular technology that allows sensors to talk back to a centralized place and give us many points of measurement. Whereas in the not so distant past, even 10 years ago, if someone wanted to, for instance, make a measurement of water quality in Kaneohe Bay, they would have to go out there and make a measurement at a single point in time. Now we've got a sensor network out there. It's telemetering data all the time. So that availability of information gives us a lot more understanding about the nuances of how various parameters work together to set compositional attributes as well as physical attributes like temperature and salt content and particles and how many organisms are living in the water. So you can think about a lot of ways that humans impact the environment. I'll just give you some examples. And I want you to start thinking about this, because as we talk about contamination in the environment, there's very much kind of two categories and how we address them. One is there a local contamination that's affecting an area? And another is there a global phenomena that's affecting everyone? Sometimes these two things operate on top of each other. Like a local contamination can be extra impactful because of a global thing that's going on. But these are the kinds of things that are global, right? Our carbon dioxide emissions and global warming, that's affecting everyore on the planet. Not equally, but everywhere it's affected. The depletion of stratospheric ozone, again, affecting everywhere on the planet, not equally, worse at higher latitudes. But then there's things that are really very local. Fertilizer runoff, right? Think about your favorite golf course or pineapple field and the waters around them. And so, or leakage that's coming out of, waste from landfills or sewage treatment plants. Every time it rains heavy here and a sign goes up at one or another beach about don't go in the water. That's what this is. This is usually from sewage, untreated sewage. So we address these differently. And we're going to talk about how we do that this semester through setting up of what we call a control volume, an area in the environment where we're going to try and understand everything coming in and out. And by trying, we're never perfect at this, but trying to understand the interactions at a chemical and a biological level in an environment, we can at least understand what needs to change about it to mitigate whatever the problem is. So it turns out that humans are especially in urban environments, we're pretty hard on the environment. We do a lot of stuff to it so that oftentimes many things are happening simultaneously. So here's an example of something that we do physically to the environment. We can cause excess erosion. Maybe we deforest a hillside. Maybe we are constantly tilling the soil in an agricultural environment where the soil would normally be stabilized for part of the year. Maybe we're setting up a new housing development somewhere, strip all the plants off the hillside, whatever it is, what happens during the first rains after that is that we run silty water off the landscape, which goes into the water, which changes the clarity of all the surface water, right? Which therefore it doesn't transmit light the same way, which affects the temperature structure in water, it affects the aquatic ecosystems, what can live there, what can't. And as we're going to learn later in the semester, the chemistry of most aquatic systems is heavily dependent on particles. Turns out a lot of chemicals like to stick onto particles and come off of particles, change their composition on particles, and these aggregations of particles have play a really big role in the kind of fate and transport of other chemicals in the environment. So that starts out with a physical thing that turns into something that affects other things. We can also just do kind of chemical things, right? And the example here is like, well, maybe we add a material to the environment that changes its pH, it makes it more acidic or more basic, or adds food. There was a famous spill here that happened about 6 or 7 years ago where there was an old pipeline running through the harbor from the days when there was a lot of sugarcane here, and raw molasses was, I don't know why they have this pipe still, but anyway, raw molasses was being piped from a storage place on one side of the harbor to a place where ships would come and pick it up. And all this molasses leaked into the harbor. And that's just like, candy for aquatic organisms. And so cause a very large bloom, eutrophication, which is a high biological productivity, which then consumes oxygen by respiring organisms eating that stuff, draws down the oxygen, is very, very harmful for macrofauna in the environment. And it's a natural chemical, glucose going into the water, but having a major impact, at least, measurable for weeks. And these things happen all the time. So these are just a couple definitions. What's the difference between geochemistry and environmental chemistry? I think really the difference is the focus on natural environments and the impacts of human technology on environments. In geochemistry, we're kind of looking at the chemical makeup of materials and why they are that way and the story they tell us about the Earth. It could be ancient rocks, it could be the history of the atmosphere, it could be, how does magma form in the interior of the Earth. But when we get into the environmental aspect of it, we're really thinking about the surface reservoirs and in all respects the way humans and other organisms interact with natural materials and non-natural materials that we add to it. That's where the kind of human technology comes in. And so the difference is really that here we're focused on human impacts, right? Whereas up here, the idea is to try and think back before humans were impacting the planet, which is the vast majority of its history. And so to understand some of this, we have to understand some of this. So there'll be a little bit of this that we'll review in times like, how does a lake operate normally? One of the really most interesting environments that we have to look at are estuaries, which is where fresh water meets salt water at the mouth of a river. Tons of really cool chemistry there, tons of very cool biology that happens there. And this has been happening for eons. And then humans come and decide, oh man, estuaries are really cool places to put harbors or other, kind of human settlements, and oops, we're dumping a lot of stuff into the water. And so the impacts are really magnified, especially food web impacts and sort of water quality impacts. And so we understand the impacts of those by comparing to the unperturbed settings. So another thing I really want you to try to think about in your mind is, as I said at the beginning, it's pretty hard to find a pristine environment on the planet, right? But there's no anymore pristine from a has humans messed it up kind of perspective. You can find some that are pretty darn close, but you can still find these chemicals, and then you can find things that are more and more modified. And so what we're really interested in here is not just saying, what specific thing did this chemical or this action do to this environment, but how have the cumulative impacts of all the things we've done affected an environment? And I'll tell you, we'll talk about heavy metal contamination at one point, and we will find that the toxicity of heavy metal exposure for humans is oftentimes a very, very complicated function of a lot of parameters, such as generalized human health. So if you have a population that is in all other respects totally, functioning on all cylinders, very healthy, well-fed, well-housed, and another population that's stressed, poverty, impacts of war, anything like that, and you give them the same amount of contamination, the one in the latter case is going to respond much more poorly. And it's cumulative impacts of all the other things that happen in the environment. And so this is one of the reasons why, for instance, when we look at the Environmental Protection Agency and they set limits, what's the safe limit for this contaminant or that contaminant? It's oftentimes doesn't take into account these things. Sometimes we have co-contamination. Cadmium and arsenic come together. When they act together, they operate synergistically so that the threshold of contamination that's acceptable is much lower. So, obviously we live in an imperfect world when it comes to regulations. And so I think it's always incumbent on people, if they can learn as much as they can, so they can live as healthy of a life as possible by limiting their personal exposure first, and then working to help society limit everyone else's exposure. That's even better. And part of that is understanding how population dynamics, how ecosystems operate, how food webs operate, and how when humans perturb an aspect of an environment or multiple aspects of environments, there can be kind of multiplicative impacts. Think about stressed food webs, for instance, relative to natural food webs, and how a contaminant might migrate up through a food web and increase in concentration at each trophic level, a process that we call biomagnification, how that might vary in a healthy food web versus one that's an ecosystem that's heavily impacted and we're missing some members within that chain. A couple more definitions. I sometimes slip on this too, but I just want you to know what the real definitions are. We call something a contaminant when we find it in the environment in a greater than natural concentration as a result of a human activity, right? So you're always safe if you find something in the environment that's more than it should be. You're always safe in calling it a contaminant. Officially, you should only call it a pollutant when someone has determined there's a net detrimental effect. In colloquial English, we oftentimes conflate these two things. Sometimes I will call something a pollutant, even though we don't have this defined. So that's officially the term. Although I'll also tell you that this net detrimental effect thing is societally determined, right? So what we culturally in the United States may consider a net detrimental effect might be different than what people in another country or another region of the planet, another culture would consider a detrimental effect. The detrimental effects can include everything from aesthetic impacts to obvious changes in an ecosystem to pretty high thresholds, which are, for instance, human death or human sublethal effects, like, whatever, growing a third arm. And our society, I would say, doesn't take the most extreme on the planet when it makes this definition, but it's a pretty high definition, so that we don't consider aesthetics generally within our system of laws for net detrimental effects, right? We only look at them when we start to see measurable biological impacts. Now, there's something else. The book uses this term toxicant. I've never used that term myself. I usually just say a toxic substance or a toxic pollutant. But this is basically a chemical that can be shown to have a net impact on the biological functions of some fraction of an ecosystem or members of an ecosystem. And we'll have a whole week where we talk about toxicology and how we measure it. And again, it's not binary. You can have things that are have long-term impacts, they have short-term impacts, they have impacts at very high concentrations only, or impacts at low concentrations. And we'll see how this is quantified later in the semester. But there are many more substances that harm the environment that maybe don't necessarily harm the organisms directly. And so that's what the distinction between those things are. Does that make sense to everyone? Okay, so the other thing I like to emphasize is the difference between natural compounds and anthropogenic compounds. So there are completely new compounds that we've invented. Chlorofluorocarbons, for instance, freon. We invented these things in the 40s. We released them into the environment, and now they're everywhere. They contribute to ozone destruction, for instance. We find them in the deepest oceans. Polychlorinated biphenyls, probably. We don't know of them existing naturally. So the very presence, the fact that they are around in an environment means that we made them and somehow they got there. Even if we didn't mean to put them there, they're there. And this category is important and is an obvious marker of human perturbation. But most contaminants that we deal with in the environment are not in this category. They're in this category, which are naturally occurring materials that are just present in non-natural concentrations. Think about every time we dig a hole in the ground to mine out some copper or rare earth elements or any other material that's used in our modern society. There's a certain amount of waste, a certain amount of tailings, washing of stuff into the environment. Those are things that are natural chemicals that are present in non-natural quantities. Another category you could put up here are plastics, right? Microplastics, for instance. Plastics, there are polymers in nature that upon which plastics were mimicked when they were first invented. Again, there was a kind of a progression between the 20s and the 40s. That the plastics that we know today, the most common ones, were first put in use in the 50s. And they are modeled after natural compounds, but we don't know of any natural plastic compounds. And so that's another thing in that category. As you can imagine, they might these chemicals that we invent, and for a very specific reason, we put them into the environment. They aren't necessarily thinking about what the impacts of the environment are. They certainly weren't 100 years ago when kind of industrialized life started. And this is another one of these important roles of environmental chemistry, is for us to go back and rethink and learn from our mistakes about you can't just purpose build chemicals for one thing and not think about what else is going to happen when you stick it in the environment. So this is an example I just give you with a couple of questions, right? That's a lake sitting here in a completely urbanized / industrialized environment. You see there's a sign here, health advisory. It's telling you don't drink this water, don't eat fish from here. So obviously the lake is contaminated, and we think it's from metal concentration. So some of the questions you might ask is in environmental sciences, okay, is that contamination? Is that pollution? How would we tell? What things would we look for to try and understand the differences? And what type of data would we want to collect to determine who's responsible, right? Is it one particular plant? Is it the entire watershed? Is it the water treatment authority? These are, I don't expect you to answer them right now, but you can imagine that there are certain things that we can do in an environment that help us understand inputs and outputs, and we'll talk about how we measure those things, like the water flowing in and how its composition looks. But also, one of the interesting things about aquatic ecosystems is we have an archive of past environments in the sediments. So we can go down in the sediments and we can say, oh, well, what was it like 10 years ago? When I was a grad student, one of the first projects I was given had to do with oil refining off of Saudi Arabia and Iran in the sort of Gulf there. And we were trying to figure out, there were metal contaminations in the sediments, and was there a period in time when there wasn't metal contamination, and did that correlate with the development of the refineries? And so we went and looked at sediments at all different layers and found out, yeah, lo and behold, boom, there's a period of time, and it corresponded to a particular refinery that was dumping into the water. And so some things that we look at in sediments are really straightforward. Other things aren't, because there's chemical transformations that happen in sediments, especially when we have a lot of organic matter and limited amount of oxygen. We get to conditions that become reducing in the sediments, which changes some chemicals and makes them move around. And we're going to learn about that stuff too, how we look through modern environmental processes in our proxy records that help us understand if we can show that something was happening. So I know like a lot of times I come across as kind of like anti-technology. I'm not anti-technology. I use like my cell phone as much as everyone else, but I think we have to recognize that humans applying their technology, and we've been doing this for about 10,000 years, is about how long we've been altering our atmosphere. For instance, as soon as we started domesticating animals and growing grain crops, we started to change the atmosphere slowly. So we do a lot of things. We change the way materials are transferred in different reservoirs on the planet. We provide ways to improve the conditions in our lives, but we also provide a means for dramatically altering the environment. And so I think it's kind of incumbent on us to understand these things as an integrated system. Sometimes there's trade-offs. Sometimes you better do one thing, and therefore you don't do another thing, or sometimes doing one thing has a negative impact. But it's always better to go in knowing ahead of time what those impacts are. And technology can be applied to remediate problems. This is an example of a plan view of a chemical contaminant dispersing in the subsurface from what we call a point source, contaminated water. We'll talk about these when we talk about groundwater contamination. It's called a PRB, a permeable reactive barrier, where the water, you can put substances in here where as the water interacts with it, it can chemically decompose the contaminant and you get relatively pure water coming out. So another thing I like to emphasize is what we call cycles of matter, the way in which materials transform through all of the exterior reservoirs of the earth, the hydrologic cycle, the biological cycle, what we call the rock cycle, through the various reservoirs, which we'll talk about in a moment. And there are kind of chemical and physical transformations that affect the global ecosystem. For instance, how much carbon dioxide do we have in our atmosphere in a natural sense that are very predictable. They've changed over Earth history because of things like the configurations of the continents and when was the last time they came together and had a mountain building event, which changes the relief. Where are the continents on the planet? We didn't always have a landmass over the South Pole, which means we didn't always have ice over the South Pole, those kinds of things. Where the continents are, affect how the oceans circulate. All of these things relate, give us the idea of how material is, transfers between the different parts of the environment. And so we call these cycles of matter. We're going to look at some cycles in a moment. I like to emphasize that we're going to talk about what we call exogenic cycles. So exogenic means at the exterior of something, like the exterior of Earth. Endogenic cycles are stuff that happens on the inside, like things happening in the interior of the planet, which we're not going to worry about because it operates on different time scales and we're concerned about for the environment. We will use the concept of cycles to quantify environments. So in environmental sciences, we think about areas that we want to quantify. Think about that lake on a couple of slides ago as reservoirs. A reservoir is something that we can define as a fixed area in space and time that we can quantify all the, or at least attempt to quantify all the fluxes in and out of it. Fluxes are movements of materials in units of like tons per year or grams per year or whatever, grams per second, something like that. And a reservoir is a volume that contains a certain amount of stuff. So, grams of stuff, tons of stuff, and this is the motion in and out of it. And we understand how a reservoir might be changing in concentration. Something might be going up, might be going down, might be staying the same, using something called transport equations. And we'll have a whole week where we talk about these things. Transport equations include all the various ways in which materials can be impacted in space and time. They can move by diffusion. They can move by what we call advection. They can be consumed or produced by biological activity. So these equations get rather complicated, but we can usually explain pretty much everything about one of these and understand if it's operating naturally or being impacted by some unusual flux that's related to human activities by trying to quantify stuff. We have the concept of sustainability And sustainability is basically the notion that a reservoir, whatever we define it to be, it doesn't have to be something of water, it could be a forest on a hillside, doesn't change appreciably in size over human timescales, right? So there are ways of interacting with an ecosystem that is sustainable, where you take something out and it's replaced on a time scale that is either long relative to human activities or substantially replenished during human time scales so that the impact is minimal. And it's really just comes down to the numbers, right? It's like, how much are you going to take out and how much are you going to put back? And when you put it back, are you putting it back in the same quality and form as when you took it out? And that's really all this boils down to in a nutshell. Of course, there's much more entailed in the concept than that. But I think if you try to think about stuff by the numbers, and then if society decides it wants to operate non-sustainably, at least they've made that decision consciously, right? They're going into it and saying, well, you know, we're giving up on this thing because we want whatever it is that we're taking from the environment more than we want that thing. And hopefully consult your population. So this is the definition of reservoirs. They have any physical subdivision of the world that operates semi-independently. And for instance, we could say the hydrosphere, which is the location of all water on Earth. Or we say the exogenic hydrosphere, which is only the surface water. Or we can have sub-reservoirs of the hydrosphere, such as a lake or the oceans or whatever. So the idea of reservoirs are very context specific. You set up a problem, you say what your reservoirs are going to be, and they may be different than the next time you define reservoirs for some other problem, but they're these definable places. The definition of cycles are the pathways and rates of material or energy transfer between reservoirs. And in a perfect world, a reservoir, a cycle is closed. It's kind of like the cycle of your checking account every month, right? Hopefully it's the same amount of money goes in, same amount of money goes out. It doesn't get out of balance in the perfect world. That's the same way we do cycles. Although there's many more inputs and outputs to a particular kind of reservoir. And sometimes we don't know the answer to each thing. They're hard to quantify. So oftentimes people will write cycles as if they're closed, meaning we don't lose any mass or energy in an environment. We try to account for all of it. And then if we measure it over a few years and it's imbalanced, we try to perfect our understanding of it and look at what things are out of balance. Biogeochemical cycles, it's kind of an old term that you see people use where it's the interaction between chemical cycles and biological life. I happen to believe that pretty much every interaction that happens at the surface of the earth at a chemical level is impacted by organisms. There's pretty much no settings until we get to the temperature or pressure conditions where organisms don't exist anymore, at least our current understanding of them, where we don't have impact by organisms. And so this kind of fundamentally impacts the way we think about things, because all the parameters that affect, especially microorganism populations, such as the availability of substrate and space and nutrition for microorganisms to operate, affect the rate and magnitude of chemical transformations in the environment, right? In a completely abiotic planet, we put chemicals in the environment, they do something different than in an environment that's full of organisms. So I think I'm going to stop there and ask if you have any questions. There's a few more slides that we won't get to today, and I actually have already a little topic video on cycles of matter, examples of how we use these things, which I'll put up there on La Lima, and you can look at. And if you have questions about it, we can talk about it next. Yeah.
How is a contaminant not net detrimental?
So think about, for instance, a dye, right? A colored substance that gets released into the water, like whatever, a paint. There are things that organisms can take in that doesn't affect them, and it doesn't affect anything else in the environment, maybe other than aesthetically. Mm-hmm. So there are a lot of things like that. Certain gases, for instance, you can have extra quantities of some gases that they're there, we can measure them, but we don't at least know of any negative thing that can happen from it. salt content within some range of parameters. You can make water a little bit saltier, you make water a little bit hotter, but it doesn't necessarily take it out of the parameters of kind of what organisms in the environment can handle. Those would be that category. Yeah. Any other questions about anything? I hope I didn't like overwhelm with too much stuff today. No. Okay. I mean, we'll try to be kind of chill this week, introductory, and then we'll start looking at different environments and chemical processes in the ensuing weeks. Great. Well, thanks everyone.
Thank you.